So I've talked before about how traditional sharding works and the benefits that it provides. But today I'm going to talk about one of the limits of traditional sharding and a solution to that problem, which was proposed by the HyperDex paper. Traditional sharding will hash an immutable key, typically a primary key such as the ID, to determine the node on which a record should live. This works perfectly for creation, when the ID is generated and then hashed and assigned to a node. It also works for any query which includes the ID, because again, the ID is hashed and the correct node is identified. But what happens when we have queries or operations which don't come with the ID? For example, what happens when we want to query a collection or table by the name of, for example, a user? When we don't have the ID, we can't identify, we can't hash it, we can't identify on which shard or which node the record belongs. So in that case, we have to query all nodes in order to find the correct record. Right? This is what MongoDB does. But it's not ideal because it removes all of the benefits of sharding by being able to divide up resources, compute resources, storage resources effectively. We can no longer do that unless we're querying by ID. To solve this problem, HyperDex conceives a multidimensional space filled with buckets which can be filled with by a node, or identified with a node. For each attribute which you want to shard, you essentially assign a dimension. For example, here we want to shard by both ID and by name. So we give each of those attributes a dimension, and the resulting space is our bucketing space. Each axis becomes gets its own hash space. So when we want to create a record, we assign it to a node something like this. In this example, we'd hash all of the attributes we want to shard by. Here, of course, is the ID and the name. We hash each separately, and we determine where along each axis that hash brings us. In this example, the ID hashes to the second row, and the name hashes to the third column. Then we find the bucket where these hash results overlap. You can see here that it's it lines up to a bucket which is identified with node 2. That means that we allocate this record to node 2. And here's how we query. For example, if we want to query by ID only, we hash the ID just as we would with traditional sharding, and from that hash we can identify the row on which our record belongs. And this allows us to narrow down from all of the nodes that only a node in this row can have our record. So we've narrowed it down from the total of 5 nodes to nodes 4, 3, or 2. So we've almost halved. Of course, traditional sharding would identify the single node to which the ID belongs. So multidimensional hashing has been less favorable for ID-only queries here. But it does allow us to do something else, which we'll see in a moment, which is query by a range of keys, a range of attributes, and get some benefit from sharding. For example, if we want to query by name, with the traditional sharding method, you would have to check all nodes. Like I said, this is what MongoDB does. But with this example, because we've sharded by name, we can hash that name, figure out where on the hash space the name lands. That gives us a column of buckets, and we know that we can narrow down our search to just those few buckets, those few nodes to which those buckets are assigned. And that tells us the nodes which we need to check. So here again, we've managed to narrow down from all 5 nodes. Only we know that one of nodes 4, 2, or 0 will hold our record based on the hash of the name that we got. So again, it's not perfect. It doesn't give us the exact node that we need to check, but it's better than having to query all nodes, which we'd have had to do with traditional hashing when querying by something other than the primary key. Now, of course, if you query by both ID and name, or all of the attributes, to be more general, all of the attributes by which you've sharded, then you can narrow down to exactly the one node where your record belongs. You can isolate the node perfectly using only the hashes of those attributes. In our example with that record we created earlier, we've been able to isolate node 2 is where this record belongs because we have both the ID and the name. But of course, we might not want to stop there. We might want to query by other attributes. For example, email. Now, in the example we've set out so far, we don't shard by email, so you're going to have to query all nodes. Again, we lose the benefits of sharding once we go beyond querying by those sharded attributes. But we can solve that problem. We can add a dimension. We can add a third dimension here to our sharding model, and now we would have to, when we create records, hash all 3 attributes to identify where in this 3D plane, this 3D space, our record would belong. And that works in exactly the same way by hashing along the attribute along each axis and seeing finding the point where those hash points meet, just as we saw earlier. But as the dimensionality of this sharding model grows, which it does, of course, every single time we choose to shard with a new attribute, the volume of the space grows as well. It grows exponentially. And the main problem with that is that it diminishes the benefits of sharding in the first place, as you have more and more attributes by which you shard. So in this example, with just the 2 dimensions that we looked at earlier, a query for just one of those attributes, just name, was able to not even half the number of shards, the number of nodes which we need to check. Okay, so even with just one attribute out of 2 missing, we couldn't halve the number of nodes. And as the number of dimensions grow, a query missing just a single attribute means that we can rule out fewer and fewer nodes until eventually, if you want to shard by every attribute in the table, you actually, unless you query by all of those attributes, this model actually wouldn't rule out any of the nodes for you. You're still going to have to query by them all, because as the dimensionality grows, the overlap of those, say, 5 out of 6, 6 out of 7, grows to include so many nodes that it's just the same effect as if you didn't shard at all. Now, this can be mitigated, and HyperDex proposes this solution, which is to split that high dimensionality space into a number of subspaces instead. So here, for example, we had a 9-dimension space we were sharding by 9 attributes. And if we were missing just one out of those 9 attributes, so if we queried by everything but, say, pets, then we would not be able to rule out if any nodes, not that many at all. So it would be pointless to shard at all by those attributes, because you couldn't rule out any when you don't have all the attributes in the query. The solution here, by splitting that big high-dimensional space into subspaces, mitigates that problem. Each record is and each attribute that we want to hash by is still hashed just the same, but it gets an access in a subspace rather than one macro space, one monospace, you could think about it. So here it gets allocated a bucket, the record gets allocated a bucket in each subspace based on the attributes you're hashing by. And it falls into a bucket just as before, which is obviously connected with a node. And when you query in these subspaces, you do the same as before, which is every attribute which is included, you hash it and you look it up in each subspace. And from each subspace, you're going to get a list of nodes. But now you can just choose the shortest list because you know your records will be present in that set of nodes. So you could, in the ID name email subspace and the date of birth postcode eye color and same with car, pets, nationality, you hash all of the attributes present. You find those sets of nodes in which your record could be, and then from the 3 sets of nodes you choose the shortest because you know your records will be present in that one. And that mitigates the problem because that means that the effects of not having all attributes in the query is minimalized because you may still have, as long as you're querying by ID, name, and email, you can isolate by a single node. You don't need to have date of birth, postcode, eye color, and it won't affect the number of nodes whether you have those or not, because you can isolate down to 1 with just 3 attributes out of 9 now. The trade-off though is that each record will have to be stored in multiple shards, so on multiple nodes. So when a record is updated, it must be updated on each shard, on each instance or replica, or however you want to think about these shards or nodes. So that creates, of course, some replication overhead, as well as a consistency problem to bear in mind that you perform the update in one place, now you need to replicate that to another place. If you want that to be highly consistent, that needs to happen before you return the user's query response. So that may cause some delay for the user, if not just some consistency challenges about making sure you coordinate that in some way. An additional problem presents itself when you are sharding like this by immutable keys. When you shard by the primary key, it's immutable. It can't change. So once you've hashed it and you've allocated it to a node, it can stay there as long as the hash function doesn't change, for example by adding or removing nodes. But apart from those situations, it stays on the node it's allocated, it's assigned to. In contrast, when you shard by a mutable key, a changeable key like email or name, those can change. Anytime you update the email or the name, for instance, or any other changeable property, we have to rehash that attribute, allocate a new node, and then move the record from one node to another. And of course, in doing so, there could be concurrent requests happening for that same record. So you've got, again, perhaps consistency or coordination problems to think about. But really, the primary problem with having to move these nodes around is that it adds network transfer overhead and potential user delay. So although you get the benefits of being able to segregate compute power and storage resources by sharding these attributes, and then being able to query on just a set number of these attributes, does cause a couple of problems, some non-trivial problems. For example, this one of having to move records around, which is much less than ideal. But anyway, that is a pretty in-depth intro, at least, to how we might approach sharding for multiple attributes, why you would do it, certainly some downsides to doing it, and plenty of complexity around managing all of this. Like I say, so much complexity that a database like MongoDB doesn't bother. They only shard by primary key, and really prefer to do lookups but for other queries across all nodes to keep things simpler, easier to manage, and easier to reason about. So certainly there are some trade-offs, but it is possible at least to shard by multiple keys, and perhaps something bearing in mind. If you do lots and lots of read queries, especially with attributes other than the primary key, it's certainly advantageous. Write heavy, update heavy query uses of a data store lend themselves less to this solution purely because of those overheads around moving the record around, and especially queries with lots and lots of attributes going to be perfect for sharding in this way. But queries by ID, you can stick to sharding by ID only. So plenty to consider when thinking about the solution, but it's certainly an interesting one anyway, and the HyperDex paper is very interesting, worth a read. Certainly some more detail than I've covered here, but it is a fantastic solution, if not always the most practical or optimal one for your use case. Anyway, thank you for watching, and I will see you soon. If you have any comments, of course, or questions, please leave them down below. Subscribe for more distributed systems discussion in the near future. Give it a like if you enjoyed this format of video. So thank you very much for watching.